Okay, welcome back everyone. So I have been we have almost covered all the aspects of all the basic aspects or the fundamental things about the operations of transistors. We have seen two main types of transistors: the bipolar junction transistor and the field effect transistor. Okay, so in this lecture we will be talking about one final characteristics of a transistor, which is the IV characteristics or the output characteristics of the transistor. Okay, so up to now the characteristics we have been seeing were all transfer characteristics. Okay, if you remember properly, the characteristics we have been seeing were all transfer characteristics. I told in a previous lecture that in this course we will be dealing with three types of characteristics. Alright, the three characteristics are IV characteristics, transfer characteristics, and another type of graphs that we draw are waveform graphs. Alright, like you drew in half wave or full wave rectifiers or clipper clampers, what the input signal looks like and what the output signal looks like. Okay, so until now for transistors we have been drawing the transfer characteristics. What is the IV characteristics of a transistor? Okay, so usually we draw IV characteristics for two terminal devices, right? Up to now we have been drawing IV characteristics for voltage sources and current sources and resistances and diodes. Okay, all of these were two terminal devices. They are two terminals, and we drew the IV characteristics. We plotted the voltage across the device and the current that was flowing through the device. Okay, if we plotted ID versus VD, then that would be the transfer characteristics. But a transistor is a three terminal device, right? For example, if I draw the BJT, a BJT is a three terminal device. Okay, so what will be the IV characteristics of this device? I mean, which two terminals shall we consider? Okay, so what we do is, since this is the control terminal, the input terminal is the control terminal and the input is controlling the characteristics of the output, we draw the IV characteristics of the two output terminals, okay, between this and this. These are the two terminals that we use to draw the IV characteristics. So for a transistor, an IV characteristics is also called an output characteristics, because to draw the IV characteristics, what we will have to do is plot the output voltage, plot this voltage versus this current, right? This I and this V. But this is the output voltage, right? Output voltage across the transistor, and this is the output current. So for a transistor and IV characteristics, the output characteristics is the IV characteristics. So let's try to plot this IV characteristics for an ideal BJT, and let's see what happens. Okay, so suppose let me draw a circuit. I have a BJT, and let me just give a resistance here and a supply. Okay, I will definitely need a supply. All right, so how do we draw the IV characteristics of a device? Okay, how do we find the current and voltage relationship? So we connect a voltage source to the device and we start to vary this voltage, right? We will start to vary this voltage. We will give here 1 volt, 2 volt, 3 volt, and see what happens to the output. What happens to the current? Okay, so what we will need is, we will need this current IC and this voltage VCE. So the IC VCE curve, IC versus VCE curve, will be our output characteristics or IV characteristics for the BJT. Okay, so to do that we will need some parameters. Let's suppose the beta of this BJT is something, suppose beta is 2. Let's assume a value for this resistance, suppose this resistance is 1k. Okay, and suppose I will input a constant current at this terminal. Suppose I will input a current of, well, let's say 2 milliampere. Okay, so let's see what happens in this configuration if we change the value of this voltage source. Okay, so to draw the output characteristics or IV characteristics of a BJT or a 3-terminal device, what we have to do is we have to fix the current or voltage of the 3rd terminal. Okay, if you have a multi-terminal device and you are trying to find the IV characteristics between 2 terminals, then you have to fix the current or voltage of the other terminal, of all the other terminals that we have in the device. So I am fixing the current of this terminal and then trying to find the IV characteristics of the BJT. Okay, so let's see what that looks like. All right, so first of all, let's replace the BJT with its model. Okay, since this is an ideal BJT, I can just replace this with a current source and we'll have the resistance here and the voltage source here. Okay, all right, so since the input current is 2 milliampere, this is 1 kilo ohm, and the output current, since beta is 2, right, since beta is 2, then the output current will be 4 milliampere, right? Simple as that. Okay, now suppose I want to draw the ICVC characteristics. VCE and IC. Okay, suppose I apply a voltage of 10 volt at the supply. Okay, so what is the value of VCE and what is the value of IC? Okay, so IC is 4 milliampere, right? Let's draw a short table on the left side, IC and VCE. Okay, so IC is 4 milliampere, right? What is the value of VCE? What is the value of the voltage between these 2 terminals? This is the C terminal and this is the E terminal. Okay, if IC is 4 milliampere, then what is the value of this voltage? Okay, let me write that as well. Let's call that VR. All right, so I will write VR and VCE. Okay, so if my supply is 10 volt and the current is 4 milliampere, what is the voltage VR? If 4 milliampere current flows through 1 kilo ohm resistance, then the voltage across the resistance will definitely be 4 volt, right? 4 milliampere and 4 volt. Then what will be VCE? Since the supply is 10 volt, then VCE will be definitely 10 volt minus VR. Since VR is 4 volt here, then 10 volt minus 4 volt is 6 volt. Alright, so how did you find that? First we found the current, 4 milliampere. From the current we found the voltage across the resistance, 4 volt, and from the voltage across the resistance we found the voltage across the transistor. We subtracted the voltage of the resistance from the supply voltage. Okay, now I start to decrease the supply voltage. Suppose I decrease the supply voltage to 8 volt. Now what will happen? Okay, so if I decrease the supply voltage to 8 volt, then what will be the current? Well, the current is still 4 milliampere. So what will be the voltage? The voltage is still 4 volt. Okay, the current is still 4 milliampere. the VR is still 4 volt, but VCE will decrease because the supply voltage has decreased. So VCE will be 8 volt minus 4 volt, this will be 4 volt. Okay, now if I go to 6 volt, what will happen? As before, the current will be constant, 4 milliampere, the VR will be constant at 4 volt, and VCE will be 6 volt minus 4 volt equals to 2 volt. Okay, now if I apply 4 volt at the supply, then what will happen? Then, well, everything will be same for IC and VR, but VC will be 4 volt minus 4 volt, which will be 0 volt. Alright, okay. Now if I decrease the voltage even further, suppose I put a voltage of 2 volt at the input, at the supply, okay, 2 volt at the supply, then what will happen? Okay, if the current still remains constant at 4 milliampere, alright, if the current still remains constant at 4 milliampere, then, well, the VR will also be 4 volt, right? And if VR is 4 volt, then VCE has to be minus 2 volt, right? Because how we find VCE? We find VCE by, well, we subtract VR from the supply voltage, right? So we have to subtract 4 volt from the 2 volt. But, well, this cannot be the case, right? Because VCE cannot go to negative, because going to negative voltages means that the transistor is not consuming voltage, it is starting to supply voltage, and we already know that a transistor cannot supply voltage. Okay, so what will happen at this point? If I decrease the voltage even further, VCE will remain constant at 0 volt. VCE will remain constant at 0 volt. Then what will happen to IC and VR? Okay, if VCE remains constant at 0 volt, then IC and VR will have to change, definitely. Okay, so how will we find IC and VR in this case? Well, if VC is 0 volt, that means VCE has become short circuited. As you already know that after that point, if the voltage is after a certain point, if the voltage is constant at 0 volt, then C and D will become short circuited. Well, in this case, if C and D becomes short circuit, then what will be the current? The current, we can find the current by dividing this voltage by this resistance. Okay, so for 2 volt input, the current will be 2 volt by 1 kilo ohm, that is 2 milliampere. Okay, and this VR will be 2 volt. Similarly, if we decrease the voltage even further, I go to 1 volt, then VCE will be constant at 0 volt and IC will be 1 volt by 1 kilo ohm, that is 1 milliampere. Okay, and this VR will be 1 volt. Okay, so this is happening because, as we know that a transistor cannot supply a voltage. Okay, the transistor voltage cannot be negative. So to maintain that condition, the minimum voltage that the transistor can go to is 0 volt. So once the transistor reaches 0 volt, if you decrease the supply voltage further, then the transistor voltage will not decrease. It will remain at 0 volt. So if the transistor voltage has to remain at 0 volt, then the transistor current must change. Alright, and this current is now determined by, well, using KVL in this loop. Okay, this current is no longer controlled by the input current. Okay, this is controlled by the output loop. Okay, this is exactly like this is actually the saturation condition. Okay, so if we plot IC and VCE, what can we see? Okay, so for the first row, you can see that it was VCE was 6 volt and IC was at 4 milliampere. Suppose this is the 4 milliampere mark. If VCE was 6 volt, then IC was at 4 milliampere. Okay, if VC became 4 volt, then IC was still at 4 milliampere. This was at 4 volt. Then IC was still at 4 milliampere. Then this VC came at 2 volt. then IC was still at 4 milliampere. Then VC came to 0 volt, then IC was still at 4 milliampere. Okay, but after that point, what happens? VC becomes constant at 0 volt and IC starts to decrease. So at 0 volt, IC will be again 2 milliampere. Then again at 0 volt, IC will be 1 milliampere. Okay. Alright, so what is the output characteristics? Well, the output characteristics looks like this. Okay, so this is the output characteristics. Well, this should be intuitive. Why? Because as you can see in this graph, which part of this graph was the output current controlled by the input current? Okay, so the input current was 2 milliamperes. So if IC equals to beta IB, then the output current should be 4 milliampere always, right? So this part of the graph represents the portion that is controlled by the input. But this part of the graph, in this part of the graph, the output current is no longer controlled by the input. Okay, at this part of the graph, the output voltage of the transistor becomes 0 volt. That is the transistor becomes short circuit. Okay, so this is the active region. Okay, this is the active region of the transistor and this is the saturation region of the transistor. Okay, so we already know that in the active region the BJT works like a current source, right? In the active region, for an ideal BJT, in the active region the BJT works like a current source, and for in the saturation region the BJT works like a short circuit, right? So what is the IV characteristics of a current source? Well, the IV characteristics of a current source is like this, right? A straight line. And what is the IV characteristics of a short circuit? Well, it is like this, right? A straight line through the origin parallel to the y-axis. So if we combine these graphs, then we will get the IV characteristics of a BJT. Okay, and interestingly, this is the same IV characteristics of a MOSFET as well. Okay, so this is IC VCE. For an ideal MOSFET, if we draw the IV characteristics of an ideal MOSFET, the output current will be ID, the drain current, and the output voltage will be VDS. That will be exactly like that of the BJT. Okay, because the only difference between a BJT and a MOSFET is in the input terminal, right? In a MOSFET, a BJT is controlled by the input current and a MOSFET is controlled by the input voltage. But we are drawing, in this graph, we are drawing the output current and the output voltage. The output current and output voltage is exactly, the relationship between them is exactly the same for a BJT and the MOSFET, right? So even for MOSFETs, this is the output characteristic graph. Okay.